Bismillahirrahmanirrahim. Next topic that we are going to discuss is parallel processing, or we can say how two or more processes can be synchronized to access a common resource. Resource can be any data or any hardware. In previous chapters, we have already discussed what is a process, and you all know a process is a user task in execution. And since we have multiple resources in our system which are shared among different processes. So in this chapter, we will be talking about the synchronization of different processes in order to access a common resource in a consistent manner. What we are going to discuss in this chapter? First, we have to understand why synchronization is important in order to develop a background. Then we will proceed for the major problem of synchronization, that is critical section problem, and what are its requirements. Then we will proceed to solve the critical section problem, and we have different solutions for it that we are going to discuss, both the software and hardware solutions. At the end, we will be discussing inter-process communication, and you all know this is one of the operations that is being performed on processes. I have mentioned it in chapter 2. Let's discuss the first point in the outline and develop our background. The first point is, what is the background related to process synchronization? In order to develop a background for the process synchronization, we need to understand first point with few examples. First point says, concurrent access to shared data may result in data inconsistency. What does this point mean? Let's develop our understanding. For example, you might have used global variables. Global variables are those variables which are available to all functions, or they are shared among all functions. While local variables are those variables which are only accessible to functions in which they are declared in. No other function outside of the one it is declared in can access it. Now, for example, we have two functions, A and B. Function A updates the value of global variable, while function B uses the value of global variable and performs further calculations. General rule of thumb says only one function at a time can access the global variable, so that all the functions can obtain the latest value of global variable. But if both functions A and B access the global variable concurrently, that is simultaneously, so what will happen? The result of one of the function will be wrong, as both functions access same value of the global variable. But as we have already said, function A updates the value of global variable, so function B should get the updated value of global variable. But due to the simultaneous access to this global variable, both functions receive same value, and hence the output or data of function B goes inconsistent. Similarly, in case of hardware, since we have mostly single instance of hardware in our system, so the hardware is also accessed in order or one after another. Let's consider the example of printer. If we activate printing for more than one documents, still the printing procedure will proceed in order. This will never happen that the printer will print half portions of all the documents, as this will bring inconsistencies for all the documents. So it is very important to access the shared resource one after another in order to keep the data or results or the hardware consistent. Resource, as you all know, can be both hardware and data. Since we have developed a background, so let's move to second point in the outline and see what is the critical section problem in the process synchronization. Let's discuss the problem of critical section. Critical section actually refers to the shared resource, which can be both either hardware and data. If we have to resolve the problem of critical section, we need to keep in mind few requirements or criteria, or you can say a few conditions. Any solution that claims to solve critical section problem must fulfill all these three requirements. First requirement is mutual exclusion. Mutual exclusion states that only one process can access critical section at a time. Since critical section is a shared resource, that can be any hardware or data. If more than one processes are trying to access critical section, even then only one process is granted access to critical section while other process will have to wait. Second condition is progress. Progress states if the critical section is available and there are more than one processes that want to gain access to this critical section. So, the decision to which process the critical section should be assigned must not be delayed or postponed indefinitely. This decision should be made quickly and operating system makes this decision. Third condition is bounded waiting. This actually means to treat all the processes equally. All the processes should be given access to critical section equal number of times. If process A gains access to critical section 3 times, so process B should also be granted access to critical section 3 times. Otherwise, process B may face starvation. So, any solution that claims to solve critical section problem must fulfill all these three conditions. If any single condition is not met, still the solution is not considered valid or complete. After understanding what is the critical section problem, next point to be discussed is what are its solutions. So we will first discuss the software solutions, as you can see in the outline, and we have two solutions for it, the Decker solution and Peterson solution. So let's see both of them one by one. Let's get to the solutions of critical section problem. We have both software and hardware solutions as mentioned in the chapter agenda. For all the solutions, it is important that the criteria for critical section as discussed in the previous slide should be all met. The requirements are mutual exclusion, progress, and bounded weighting. So let's discuss first the software solutions and check if all the three conditions are being fulfilled or not. Decker proposed solutions for critical section problem, and it is a two-process solution. In his first algorithm, the use of turn can be seen. That means turn by turn processes can access critical section but not simultaneously. So if it's process I's turn to use the critical section, process J has to wait for its turn. Let's find out if three requirements are being fulfilled in it or not. First requirement is mutual exclusion. With the use of turn, it has been ensured that only one process at a time would be using the critical section, and other process will have to wait. That means critical section condition is being fulfilled here. Second condition is progress. As progress says, the decision to which process critical section should be assigned must not be delayed indefinitely. But here we can see if it's process I's turn, but I does not want to use the critical section, and it's not process J's turn, but J wants to use the critical section. So unless and until I does not consume its turn to use the critical section, process J will never get its turn to use the critical section. So even though critical section is available and there is a process that wants to use the critical section, but still the decision to whom critical section should be assigned goes pending, and this is due to the use of turn. So process J may have to wait indefinitely in this case. Here, progress requirement is not being fulfilled. I give you a simple example to this. Let's suppose we have a single multimedia, and the use of multimedia has been scheduled as per timetable of your class. Now when it's my class with you, it's my turn to use the multimedia. But I do not want to use it for one single class, and multimedia is available. If, for example, another teacher at the same time requests to avail multimedia, he or she will not be granted because it is scheduled to be in my use, but I am not using it, so other teacher will have to wait, which is not an ideal way. If I am not utilizing the multimedia, that has to be made available to others, even though it is my turn to use it. I hope this must be clear to you now. Third condition is bounded wait. Use of turn provides fair mechanism to treat all the processes equally. The number of times process I is granted access to critical section, the same number of times process J will be granted access to critical section. So, bounded waiting here is being fulfilled. But since one requirement or condition is not met, so this algorithm is not considered a valid or complete solution to critical section problem. Decker then proposed another algorithm in which the use of flag is visible. Flag here means a signal, or simply you can say a signal to show wish of a process to use the critical section. When flag of a process is set, critical section will be assigned to it and other process will have to wait. After leaving critical section, a process has to set its flag off in order to let operating system know that critical section is now available. Let's check all the three conditions here. First condition is mutual exclusion. Whoever sets its flag first will be granted access to critical section and other process will have to wait. If both processes set their flags at the same time, then first come, first served policy will be imposed. But only one process at a time will acquire critical section. So here mutual exclusion is being fulfilled. Second condition is progress. The use of flag has made the decision very simple. No matter which process is standing first in queue, critical section will be assigned to only that process whose flag will be on. So decision will not take long and progress here is being fulfilled. Third requirement is bounded waiting. Bounded waiting goes disturbed because if only single process requests critical section again and again by setting its flag, so one process may get more chances to use the critical section as compared to the other. And fair treatment policy of bounded waiting goes disturbed. Hence, bounded waiting here is not being fulfilled. Again, one condition is not being met, so this is again not considered a complete solution to critical section problem. After multiple failed attempts by Decker, another solution was proposed by Peterson. Peterson actually merged both the algorithms of Decker and made sure the use of both turn and flag simultaneously, which has been done separately in separate algorithms by Decker. Let's see the Peterson algorithm. It uses both turn and flag, as you can see in the algorithm. Both the conditions must be true in order to get the critical section. Again, it's a two-process solution. Its state: it has to be a process turn and its flag should also be set. Only then critical section can be assigned to it, otherwise not. Let's check all the three conditions in it. First condition is mutual exclusion. Mutual exclusion is being fulfilled here clearly, as at a time there has to be only one process turn, even if both the processes may have set their flags. But the critical section will be assigned to single process at a time, the one whose flag is set and its turn is also to use the critical section. Second requirement is progress. Use of flag simplifies the situation. So if both processes are waiting for critical section, the decision as to whom critical section should be assigned can be made very quickly. The one whose turn is to use the critical section and its flag is also set will only be eligible to use the critical section. So progress is also being fulfilled here. Third requirement is bounded waiting. Bounded waiting is also being fulfilled here with the use of turn. Number of times process I will use the critical section, so same number of times process J will also use the critical section. Since Peterson solution fulfills all the three conditions for critical section problem, so this is considered a complete or valid solution to the critical section problem. That is all for now. I thank you all.